In this video, I'll talk about the convergence of a multi-step method. Like before, we'll look at the initial value problem, dy dt is equal to fty, and we have our trifecta: consistency, convergent, and stable. So in this notable, we'll say that is not convergent or non-convergent. But first, let's define convergence. The solution of the multi-step method wi is said to be convergent with respect to the exact solution of the differential equation if, as the step size goes to 0, for all I that we're interested in solving, then the exact solution minus the approximation will equal 0. So it means that the exact and the approx tend to the same thing. This is true for all Runge-Kutta Adams methods. So like in the previous video, I'll introduce the Abysmal-Butler method because it's not convergent. It wasn't consistent, and that's why it's not convergent. But it's a nice illustration. Once again, the two-step Abysmal-Butler difference equation is given by wi plus 1 is equal to wi plus h divided by 2 y fti. And as before, the exact same differential equation, y dash equal to t minus y. Reading in our libraries, defining our function. Now, the difference here is I want to show that actually it's so important to know that something is convergent or not convergent because it can be internally convergent, as in it can converge to a solution, but it will not converge to the exact solution if it is not convergent. So to do that, I have to illustrate this by doing two types of mesh. We have a coarse mesh and we have a fine mesh. Coarse mesh is n is equal to 40. A fine mesh is n is equal to 32. Actually, 16 and 32. So here we have the coarse mesh and the fine mesh. And what we have to do is compare the solutions at the coarse mesh points. Now that'll show that actually the error is going down, that the solutions are approximating each other well, but that they're not doing the right thing. So our two-step Abysmal-Butler method is easily rewritten as wi plus 1 is equal to wi divided by h, and then we insert the right hand side of the equation for fi and fi minus 1 are 4 ti minus 1 minus wi minus 1 and 3 ti minus 1 minus wi minus 1. Yeah. As before, we have to be very careful because if we start as I is equal to 1, we can't solve because of this. So we have to start as I is equal to 1. W2, which means we have to approximate W1. Now you can approximate that using a one-step method, or in our case, we use the exact solution. So we set up our initial conditions, we have our fine mesh loop, and we have our coarse mesh loop. In the coarse mesh, I'll use actually the solution from the fine mesh to approximate. So now here we have our solutions. That's the exact solution. The fine mesh and the coarse mesh have similar shapes, and actually if I keep on increasing the n here, they'll actually get closer and closer to each other, but it won't get closer and closer to the original, and that's why they're not convergent to the exact solution. They're convergent to a solution but not the exact solution. So how do we show that something is convergent? We have to show that it satisfies a Lipschitz condition, which shows internally convergent. So we have f minus ft hash. And so we do our little calculation, we work our way through, and we show that this is internally consistent. Yeah, it converges to the same solution, but it is not convergent. Yeah, it isn't convergent because the exact solution and the approximate solution do not tend to each other. And this is because, like we saw earlier, that the tau for the consistency is not satisfied. It doesn't tend to 0, so there'll always be a gap between the exact and the approximate solution.